Electrochemistry, Part 3, Cell Potential and Free Energy. In this video, we will explain whether an electrochemical cell is thermodynamically favored based on its standard cell potential and the constituent half reactions within the cell. The derivation of this relationship between free energy and cell potential is not important, but it's probably in your textbook somewhere if you're really interested. The relationship shows us that the standard Gibbs free energy change is proportional to the negative of the cell potential for a redox reaction from which it's constructed. Therefore, a cell with a positive cell potential, that is a galvanic or voltaic cell, will have a negative delta G and is therefore thermodynamically favored. A cell with a negative cell potential, that is an electrolytic cell, will have a positive delta G and is therefore not thermodynamically favored. A cell with a cell potential of 0, in other words, a dead cell, will have a delta G of 0 and is therefore at equilibrium. The quantitative relationship tells us that for a redox reaction, delta G naught, the standard free energy change, is equal to negative N, the moles of electrons transferred, times F, Faraday's constant, times E naught, the standard cell potential. The number of moles you use is dependent on how many moles of electrons you got to cancel out when you added the two half reactions together. And Faraday's constant is 96,485 coulombs per mole of electrons. Now, let's see if we can't use this relationship. For this problem, determine the standard free energy change and predict the spontaneity of the electrochemical cell for this redox reaction. Reduction half reactions and their standard reduction potentials are provided. Go ahead and pause the video and see what you can come up with for yourself. To determine the standard free energy change, we'll need to figure out the cell potential. To do that, we'll need to flip one of these half reactions. Since we were already given the overall equation, and we don't know if this is going to be a galvanic or an electrolytic cell, we'll have to flip the iron half reaction so that it matches up with the overall equation. We'll change the sign of its half cell potential too. It looks like our electrons will cancel, so we're ready to add them up. Our overall cell potential is positive 0.78 volts. That means we've got a galvanic cell on our hands. Hopefully, not literally on our hands, because then we'd need to go wash them. Anyways, now that we've got the cell potential, we can quantitatively determine the standard free energy change. Using the free energy cell potential relationship, delta G equals negative NFE, we have delta G naught equal to negative 2 moles of electrons from the balancing of the two half reactions times Faraday's constant times positive 0.78 volts. Since a volt is defined as a joule per coulomb, we'll end up with joules as our unit and negative 150,000 joules is our answer. That's a negative 150 kilojoules per mole of reaction. That's hecka favored. Recall that a negative standard free energy change means that under standard conditions, this reaction will increase the entropy of the universe and is therefore considered thermodynamically favored in the forward direction. Of course, we already knew that because a positive cell potential told us that it was a galvanic cell. Galvanic cells, by definition, are thermodynamically favored in the forward direction. So now let's try to use our electrochemical understanding to make a prediction about something that is a redox reaction, but isn't actually an electrochemical cell, because it's all in one beaker. Let's determine the free energy change under standard conditions and predict the spontaneity of dissolving gold in excess nitric acid, using the equation and half reactions and reduction potentials provided. Let's say you accidentally dropped your gold ring into a beaker of concentrated nitric acid. Should you worry about it reacting? Go ahead and pause the video so you can solve this one on your own first. In order to get gold to be a reactant, we had to flip the gold reaction, half reaction, and make it oxidation. That's why we changed the reduction potential sign to make it an oxidation potential. By the way, since we flipped the half reaction that had a more positive cell potential, this is akin to an electrolytic cell. This is not going to be a thermodynamically favored process. But let's continue so that we can determine the free energy change. We'll need to sum the cell potentials, giving us an overall cell potential of negative 0.54 volts. Plugging in the N, the F, and the E to our equation gives us a total of positive 160,000 joules, or positive 160 kilojoules per mole of reaction. Dissolving gold with nitric acid is a non-spontaneous process. That means your gold ring is safe. And it is unlikely that anyone will try to steal it since it's at the bottom of a beaker of concentrated nitric acid. In this video, we looked at how to calculate the standard free energy change for an electrochemical cell. This allowed us to predict spontaneity. Luzio out.